let me start, please, with introducing a little bit why kind of we're concerned with Antarctica. So a little bit of background here before we move into seeing some beautiful pictures from a continent very close to my heart, and I know very close to some of your heart as well. So when we look at our planet Earth, we of course feel that it's warming now, and it's been warming for a while due to the increased amounts of CO2 we put into the atmosphere. And that warming has now last year surpassed the 1.5 degree mark, which is a mark that people many years ago in Paris at one of these climate conferences agreed to ideally not step above. So that was just 1 year. It doesn't mean we have globally kind of overstepped that mark now, but we're getting very close to it. And you can see in the dark red colors that our planet is really warming more in the northern hemisphere because there's more land and more over land than more over the ocean. When we think about the consequences of that warming, there's of course many, and here in the UK, we definitely see kind of increasing heavy rainfalls leading to floodings. In other parts of the world, we see more wildfires and droughts, increased hurricanes. But what I want to talk about today is really the melting of ice, and that's where my favorite continent, Antarctica, comes in. So when we think about the ice, I think those of us who have been kind of in the mountains or live close to the mountains even might have even witnessed in our lifetimes that kind of glaciers are retreating, and they do so quite dramatically. This is just one picture from the Quilcaya ice cap in Peru. But when we think about the total amount of ice on our planet, the big players really are in the north and in the south. So it's Greenland and Antarctica. So today we have an amount of ice sitting on top of Greenland that if we would melt all that ice, sea level would go up 7 meters. And if we look down at Antarctica, the total there is 58 meters. And that's a huge number, and it's often very abstract to people. So I like to bring it back home to London, in my case, where I live. So here are some of our landmarks, the London Eye and Big Ben. And if we add up all that ice that is on our planet right now on top of the poles, if we would melt that, it would basically bring global sea level to half the level of the London Eye and above the clock of Big Ben. So just kind of a reference, the Greenland ice sheet, the 7 meters, is about the diameter of the clock of Big Bang. So that's kind of how much ice we have, how much water we have tied up in ice on our planet right now. So a lot of people might say, well, it's a big step to think about the world we're in now and removing all of this ice. Has this ever happened? And I think this is where everybody like me who has a background in geology will say, of course, we can just use the geological past and kind of look at it. Here in the UK, if we just go to our south coast, we look at the cliffs, the White Cliffs of Dover or any equivalent there, they're made out of chalk, and that means that was a shallow sea environment when that sediment was deposited. And on the time scale here, you can see that that happened in the not too distant geological past, some 100 million years ago or so. So we had a shallow sea environment here, and our planet basically had much higher sea level, but it also was much, much warmer back then. So from reconstructions, we know that it was about 10 degrees warmer than today, so quite a bit warmer. So we're not heading there quite yet. So where are we heading? Well, this is a little movie I want to play now, and I hope it works. There we go. This shows you the ice loss happening in Antarctica over the last 20 years or so from satellite observations. So the blue curve, where you can see the red circle kind of moving along, is time moving from left to right, and the y-axis shows you mass loss. And on the continent, you can see in red, coloring in the areas where the most pronounced ice loss is happening in Antarctica right now. So the darker red the colors, the more pronounced the ice loss. And you can see that the area which gets most pronounced in terms of the ice loss is an area kind of to the left-hand side of the slide here, which is West Antarctica. So that's where most of the ice mass loss is happening right now. So the big question is, do we know why? And the short answer to this is we start having a very good understanding why. So in the middle here, you could see a picture of Antarctica, again, with its separation in what we call the East Antarctic Ice Sheet, so the big chunk of it on the right-hand side, and then on the left, the smaller part of it, the West Antarctic Ice Sheet. But that by itself holds 5 meters worth of sea level rise as well. And you could see for reference an outline of the UK here. So the ice is on average like 2 kilometers thick or so on Antarctica. On the right-hand side, you see a snapshot of this observed ice loss I just showed you the movie about. And on the left-hand side, you can now see why that is. So the left-hand side shows you the continent. If we would remove all the ice that sits on top of Antarctica, that's what the land would look like. So wherever we have green and brown colors, that means the continent is above sea level. And wherever the colors are blue, that means the continent stays submerged below sea level. And you can see that pretty much most of West Antarctica is in the blue colors. So it's a continent that's submerged below sea level. We call that a marine-based ice sheet. And that means it can not only melt top down by warming of the atmosphere, but it also gets eaten up from below. So warming ocean waters can get underneath the ice shelves and eat it up from below as well. And that's why it's so much more vulnerable than the bigger neighbor in East Antarctica. So that is kind of the status quo. But if we look now forward into our future, we have to realize that the observational data we have of the melting of the Antarctic ice sheet and how quick that might happen and what the mechanisms are only cover, a couple of 100 years or so. We can't really see extents of warming of what we might be expecting. And the thermometer here shows you a snapshot from a website called the Climate Action Tracker, which shows projected temperatures by the end of the century, so by the year 2100. And the blue box shows if we stick with all the policies and actions around the world we have in place right now, we can actually expect a warming of 2.7 degrees Celsius by the end of this century. And if you step then towards the right down these boxes, you can see in the most optimistic scenario, if we kind of stand up to all our pledges around the world again, we might keep warming just below 2 degrees, which is of course what we're all hoping to do. And the question then is, if that is kind of what our future looks like, what does Antarctica do under these conditions? And this is, again, we're looking back in Earth's history, becomes a very powerful tool. So if we go back in time, we had times in the past when the planet was warmer, as we've seen, for example, going all the way back when we had the shallow sea here in the UK. We also had times when it was colder. And so we could find these periods where temperatures were just 1, 2, or 3 degrees warmer, depending on what exactly we want to study. And I just listed here a couple of examples. For example, the last interglacial period, 125,000 years ago, was 1 to 1.5 degrees warmer than today. And the Pliocene warm period was 2.5 to 4 degrees warmer than today. So these are periods which are in that window of what we expect by the end of the century. And those are the periods we really want to understand and study, because we fundamentally don't know how Antarctica reacted in some of these periods. So how do we go about that? Well, we need to step back in time. So, you can think about it wherever we are sitting in our built environment. If we look at the Earth below us, of course, there's wonderful layering, and the further down we go, the further back in time we go. So it's basically stepping back in time to find those right intervals to learn about Antarctica. So the key question I really want to get to, and our project I will introduce you in a minute to, wants to get to, is how much ice will melt with future warming, and how fast will that happen? This is really a question with implications for sea level and all of us around the world. So it's really important for humanity. And our mission here as scientists is really to just help with the adaptation and mitigation efforts by figuring out under which environmental conditions, in this particular case, the West Antarctic ice sheet will completely lose its mass. So when will it melt, basically? That's the question I want to kind of dive a little bit into today. And as Rod kind of mentioned in the introduction, the project, which has kept me quite busy over the last few years, is called the SWAIS2C project, which stands for the sensitivity of the West Antarctic ice sheet to 2 degrees warming. We have a website as well. I give kind of the link here. I have it later on in the show. So if you kind of type it into your search machines, you can easily find it. And there's lots of background material about our project. And the top picture shows you a first glimpse of what our camp in the middle of nowhere in the field looked like. So what is that project? So the SWAIS2C project is basically a project which targets 2 sites on the Ross Ice Shelf to retrieve 200-meter long sediment cores. So cores to look back in time to reconstruct Earth's history. The sites you can see on the map here are on the eastern side of the Ross Ice Shelf. So the Ross Sea, you can see in the smaller picture here, is kind of the sea separating East and West Antarctica. There's a big ice shelf on top of it. And for orientation, for those of you who are not used to looking at Antarctica all the time, it's basically closest to Australia and New Zealand. So we're looking at that part of the world. And our 2 sites are shown by the red circle and the blue circle. And we picked these 2 sites because one of them is basically an ice shelf where there's a bit of ocean underneath, and we wanted to drill underneath there to see the effect of that warming water coming underneath the ice shelf. What does that do back in time? And the second site is a site where 2 very fast flowing glaciers meet. So it's basically looking at the stability of these so-called pinning points of the ice sheet. So that is the sites. How did we want to go about it? Well, it's a combination of hot water drilling and sediment drilling, and I will show you and explain you a lot more about that one. And who is we? Well, we is a very large international consortium. There's over 100 scientists involved from 10 nations who are participating. I think if you look at the nationality of all the scientists, there will be many, many more than just the 10. The whole project has been more than 10 years in planning, and funding comes from a large variety of national funding institutions and individual institutions in different countries. And you can see them all shown at the bottom here. So we are very grateful for all this long-standing support. So this is a little cartoon for our first drill site, which is called KISS because it stands for the Camp Ice Stream. That's the ice stream going into the Ross Ice Shelf. And the cartoon here comes from an article which was published last year in the Sunday Times just before I went out and talked a bit about how I will spend my Christmas on the ice this year. So you can find that if you look back at your archives. But at this site, the ice shelf, the floating ice, is about 600 meters thick. It's exactly 580 meters given here as the number. Below that, you then have 55 meters of ocean. So the ice floats on water, and that water is a little bit tidal as well, which is for drilling quite challenging. So the water goes a bit up and down. And our goal was to then drill 200 meters into the mud below the seafloor. So this is where that archive of the history of the Antarctic ice sheet is preserved. And on the right-hand side, you can see exactly how this works. So the top panel shows you an ice shelf situation like today, so floating ice over the ocean, and then you get a typical type of sediment which is deposited underneath, and that's what we can find today. If you go in a situation where the climate was colder and ice fills up the entire space, so there's no water anymore, it's grounded ice as we call it on the continent, you get a different type of sediment. It's a diamix, so it looks very different and you can visually identify it straight away. Equally, if you go to the other extreme and go to a time where all of the ice might have melted in Antarctica, so you don't have a Ross Ice Shelf anymore, and the West Antarctic Ice Sheet is collapsed, what you would get is basically open ocean conditions, and you get deposits of marine algae, which kind of get this characteristic green color here from the diatom oozes we find around Antarctica today. So just by basically retrieving the sediment and looking at it, we would already learn tons. And then there's, of course, a lot of sophisticated analysis we can do later on. So this is kind of the quest. So we went out and we did 2 field seasons so far. So I've not only been on the ice once, I've actually been there twice by now, in the last 2 winters. We went to this KISS 3 site, and I think the first thing to say for everybody who's never had the privilege to go to the beautiful continent down south, it's not an easy place to get to. So from the UK, it's, you know, if you're lucky and your connections work out, it's a 30-hour flight to get to New Zealand. All the aircraft down to the continent are then operated out of Christchurch. So you fly to the South Island. And then depending on what aircraft you go, and I show here 2 of them, the C-17 at the top is the big US Air Force aircraft, and then at the bottom is Hercules, a smaller one. It takes like 7 to 9 hours to actually get from New Zealand down to Antarctica. And you basically fly in cargo machines. So you sit in between kind of a lot of cargo that gets flown down there. So that already takes quite a long time. Once you arrive down south, I think everybody who has been will say you never forget that moment you first touch down, that when you step off that airplane and put your foot on the ice, it's absolutely a magical environment. Of course, nobody permanently lives in Antarctica. All the bases are for scientific purposes, and the population increases a lot during summertime when all the science is done, and shrinks a lot in the winter when just basic maintenance and some science continues. So at the bottom right, you can see pictures of Scott Base, which is the New Zealand base in Antarctica. So I deployed through the New Zealand program because they do all of the logistics together with the US program, which has a base station across on the other side of the hill, McMurdo, which is 10 times the size of Scott Base. But it's basically container villages on the ice. So the green buildings are all the buildings there where you live and sleep. And when you first arrive, what they do with everybody is do the so-called Antarctic field training. So they put you in a vehicle and drive you like an hour away from the base station. And then you kind of put up a tent, you kind of cook your own dinner over a stove, and you sleep out there in your tent overnight. And they do that to test whether you kind of psychologically fit for going to the deep field. The physical tests all have to be done before that you're medically deemed fit, but it is quite an interesting thing when you come out there the first time. It is, you know, minus 10 degrees or so, and somebody tells you you'll have to sleep in a tent for the next 6 weeks. You do wonder how this all works. So it's good that they do good training, and close to the base station, you get the fortunate situation to see a lot of seals as well, which are really cute, I have to say. Right, so our field site we then wanted to go to, as you've seen from the map, is far away actually. It's on the other side from the Scott base. So it's 800 kilometers as the crow flies away. So the heavy gear, we had to actually get to our site in these piston bullies you can see on the map here. And at the back there, you could see a big blue container. That was one of our science laboratories. You can also see all kinds of other stuff. So the piston bullies drove for 2 weeks across the ice shelf, more than 1,000 kilometers. And again, thank you and shout out to the logistical support from Antarctica and New Zealand. They did all of that. So 6 people drove all our stuff across the ice shelf to our site. The scientists, drillers, and engineers then went onto these little airplanes shown on the top left there, the Barcellas, which were provided by the US program. So again, it's a really cool international collaboration we're doing here. That meant our trip was, instead of 2 weeks, 3 hours, which makes a huge difference. And this is what the site looks like when you arrive. I would say it's the most beautiful impression of nothingness. It's just flat ice in all directions as far as you can see. In the summer, it's 24-hour daylight. So that picture is the same picture all day, every day. There's just nothing, and the reflection of the sun in the ice is one of the most stellar and beautiful things to have the privilege to experience. But where we needed to go is from that kind of situation to something like that. So in the top in the middle, you can see one of our science tents where all the scientists basically sit and look at their computers, a bit like we're sitting now in our offices, and that in the middle of nowhere in Antarctica. On the top right, you can see a picture of our drilling tent. So all the pictures from the drill tent will always be very orange because it was an orange tent. And then at the bottom, you can see our mess tent where we, at that particular point, have one of our morning briefings. And the picture is taken from the perspective of a little corner where the kitchen was. Quite a social space, and it was one of our two warm spaces in the camp. So what you have to do when you get down there, it doesn't matter whether you're a scientist, an engineer, or whatever your upbringing is and your passion is, you're just a pair of hands, and you have to build up camp first. So in the top row, you can see mostly the drillers in this case actually putting together the drill tent from scratch. And then at the bottom, you can see some of the scientists putting together all our sleeping tents. So we had individual sleeping tents, either the pointy ones, the Scott Polar tents, or the round ones, which are the dome tents. And then at the bottom right, you can see our mess tent, which is what our social space was, where it was warm as well. So it wasn't warm in all of our spaces. And this is my new favorite picture. This is a drone picture we took this year of our camp on a nice sunny day. And I will talk you through what you see, but it gives you a wonderful impression how we were literally in the middle of nowhere. And at some point, it dawned on all of us that the closest people to where we were actually people at the International Space Station, because that's only 400 kilometers away, up in space, of course. And Scott Base was 800 kilometers away. So that was just an interesting kind of realization we had at that moment. So you can see at the top left there in orange, our big drill tent. Next to it, the blue box is a container we had basically to do very clean laboratory work in, our warm science container. The two yellow tents there with the arrows now were, one was a warm tent, so we could leave our computers there and they wouldn't die in the cold. So as I said, it was on average minus 10 degrees or so. And the right one was a cold tent where we just staged a lot of our supplies. The big yellow tent over there is the mess tent, so where we had our meals and our briefings. Then the kind of battery of green things there is the piston bullies, which drove everything out. And there is a green container as well, which is a living module from Antarctica and New Zealand. And that's where the doctor lived. So in case there's medical emergency, you obviously have to have facilities for that kind of out in the middle of nowhere. And then we have our little tent city where everybody had their individual sleeping tent, so you can count the tents. We had like 26 people out there this year. And then there's another little blue box I circled here now. So what's that little blue box? Well, the thing nobody ever talks about, but everybody wishes they would have talked about beforehand when you go the first time down south. It's the toilet situation. It's always a huge issue. So the blue box was our toilet box. So you basically have a bucket with a seat on it. That's the toilet situation when you work down there. And the picture in the middle is all of us in our first season lining up in front of our toilet, because we tried to make the point to our logistic providers that one toilet is not enough for 26 people. There are certain crunch points of the day and you want more than one toilet. So what we did in our first season is we built ourselves a second toilet, because you get quite used to the cold after a while. So we had an outdoor toilet as our second toilet. So we just built a wall around it for some shelter. And we called it the Nautilus because it has the form of a Nautilus here. One of my biggest wins, being the chief scientist of this expedition, is that when we went again this year for our second season, they listened to us and we actually got a second toilet. So, you have to take the wins as they come. So there's a blue box in this picture now, which is our second toilet. And again, a nice little detail and a real kind of luxurious item we had is because we did hot water drilling in our drill tent, we had a little corner where we installed a shower as well. Because we had hot water, we could actually do some showering, which normally when you do deep field work is a total no-go. You just don't shower for weeks and weeks. That's just how it is. Okay, but I want to talk a little bit about the science and the drilling now. And I think this picture gives you a taste where this is going. Drilling in Antarctica is a rather challenging endeavor. And I think everybody who tried to do field work in polar environments is very familiar with this. When we do things here, kind of in civilization, if something doesn't work, you pop around the corner to a shop or you call like an engineer and get some help, get a spare part. Everything is relatively easy. When you're in the middle of nowhere, nothing is easy. So in the first season, the 23-24 season, the riser material, which is basically the outer pipe in our drill hole, kind of the material we used for that was not suitable for the environment, even though we did extensive testing at home. So the season kind of failed before we even got going. So we learned our lesson from that, ordered traditional drill pipe, steel pipe, and then went back for the 24-25 season. So that was just last winter. And this time we unfortunately had the situation that in the first few days of putting kind of together the drill rig and our camp, a very critical component on our drill rig that rarely ever breaks, the shaft of the hydraulic motor sheared off. And that was really, really unlucky. And we had a whole investigation into it afterwards. These things can happen. You can't prepare for every eventuality. We did order a replacement part, but that had come all the way from Canada, and it went from Canada to the US to New Zealand to the base station. To cut a long story short, it didn't make it to the field in time to actually help us with the drilling. So that was a big kind of problem. A second thing we had is actually a lot of success and then some more failure. And that's just the story of Antarctic fieldwork. So in our field season 24-25, we managed to deploy 630 meters of sea riser. So this outer tube we put through the ice and the ocean to have basically a conduit to then deploy our drill string in. And you can see on this slide here on the left, a picture of our drill rig, and the big blue thing basically is the chuck. So that's a clamp which holds the drill string and the pipe. And then in the middle, you have a foot clamp, which is a second place to hold it. And my colleague, Richard Levy, and his wife put together an absolutely stunning little video which shows you what happened next then. So after we deployed our sea riser and tried to deploy the drill string inside the riser, we managed to do that really well for a bit. And here's the process. So you have 3-meter bits of steel pipe, and we use drawers in this example, and you can see Richard's hand going up and down. So that's the chuck and the foot clamp kind of grabbing bits of steel, then you lower it into the hole, you connect the next bit of steel, you open the upper one, you close it, you open the lower one, and that's what you shouldn't do. You shouldn't open them both at the same time. So unfortunately what happened is both clamps were open at the same time, and you could see the result is, like with the straws, we dropped the drill string. Not a good idea to do, but I think, again, everybody who has been involved in drilling operations has seen this happen. It's just when it happens in the middle of nowhere, it's really, really hard to recover from this. The good message for everybody is we showed as a proof of concept that it all can be done. We were just a couple of hours away from getting our first drill core there it drops again, when we dropped the drill string. But the key thing is nobody got hurt. We're all still talking to each other. So it's all good, important lessons learned for the future. I want to kind of highlight some of the successes before I kind of wrap up. And they're really no meager feats. There's entire expeditions who just do the things I'm showing on the next few slides now and don't even try to attempt this ambitious drilling we try to do. So what a lot of programs do is they do hot water drilling. So you can see here a little cartoon again on the right-hand side. So to remind you, we have about 600 meters of floating ice on 50 meters of ocean. So what we do first is we have to melt a hole through that ice. And the way this is done is by shuffling a lot of kind of snow into these kind of yellow swimming pools. We call them flubbers. At the end of the season, they sometimes double as swimming pools as well, but you know, that shall not be documented. And that water from the flubbers then gets put through kind of some tubing through boilers and gets heated up. And then it basically goes into something which looks like a big garden hose, and you just point it at the ice shelf and start melting a very small diameter hole. And then you gradually widen it till you have a 35 centimeter diameter hole. So that process is very challenging. And the team from New Zealand, who actually used technology from the British Antarctic Survey for this, have really perfected that over the last 10 years. So we very successfully made a hole through the ice in both of our years. And once you have an open hole, you can actually start doing some science. So you don't necessarily have to kind of target the deep drilling. What we first do is we basically do a lot of like basic observations. So at the bottom left here, you can see a thing we call a gravity core, which is just a hollow tube with a lot of weights at the top. And you basically lower that through your open hole and let it slam into the seafloor. And then you pull it back up. And you can see here it's full of mud. So there's a meter or so of mud in it. So this is a picture from this here. You can see me in the picture there as well. And at the top, you can see a kind of 2-meter long sediment core, which is from the year before. So we collected a lot of these shorter cores. So we have a lot of the mud from that area now, just not as far back in time as we initially wanted. And then in the field, we used our science container we had out there to do a lot of very clean sampling. So you can see one of my colleagues here completely suited up for clean sampling to look at things like microbial activities, ancient DNA, and the waters kind of down there. So all of that was very, very successful. The the upside of actually drilling of ending our drilling operations a little bit early because it happened just a couple of days before Christmas in both years. Well, I should start with the downside. The downside is there's no operations. Everybody is having a Christmas break. So you're stuck in the field. Nobody comes and collects you. But the good thing about that is we were all expected to work in 24-hour shifts. And because the drilling didn't happen, we actually had some spare time. And our cook, we had a wonderful cook out there. You can see in the picture top left, Elle, really was absolutely amazing in the cookies and meals he provided. And so we had a proper Christmas meal out there, which was really nice. And you can see in the picture my co-chief scientist, Richard Levy from New Zealand, and myself there in our Christmas gear. And on the right-hand side, you can see some of our science colleagues engaging in a photo app. So they were working in the clean container in full body suits. And then we're joking how cool it would look to stand in a white suit on the white background. And here we go. So we did some fun pictures as well. We then made it back to Scott Base. And as somebody who hasn't been in Antarctica till like 2 years ago ever, high on my bucket list was to see some penguins. In the first year, I didn't see any. And that was my highlight of the second year. It was literally the day before we flew back home. Just outside the base station, there was a lot of Adelie penguins running around. And you could see them kind of doing their penguin walk. Just really cool, very cute. So I finally got my penguins, which was a big win on my list as well. But importantly, what's next for the science? So we brought our drill rig back home because after kind of the challenges we had out in the field, there's a lot of checks we wanted to do. We had an independent investigation by engineers into our technology to make sure we're not overlooking anything. They said we're all good. There's no fundamental problem, but there's a lot of small modifications and tweaks being done to our rig in New Zealand right now. We will start in 2 weeks' time on the 16th of June with a 2-week session for the new drilling team, which will go out next winter to train. Because as you've seen, the operating the levers and putting the drill string together is a quite manual process. So we want to make sure we provide better training for everybody, have better standard operating procedures for everything, so that we can go out in December, and that's the plan right now, to our second drill site, and then hopefully and successfully get our 200 meters of sediment core. So in conclusion, I think we had two absolutely amazing teams out there. I'm very proud of every single person you can see on this slide, a mix of scientists, engineers, and camp people from all walks of life. I met a lot of amazing and interesting people. We work together as teams fantastically. I think we build up the knowledge now to really, really know how to do this. And we'll go again as the science we try to do really matters. Thanks for your attention.
That's fantastic, Tina. Thank you so much. I am besotted by this complexity, machinery, equipment. Sorry, I've got a phone call coming in. Let me kill that. Yes, particularly the toilet arrangements. I think you're well blessed there. Also, the fact you had tents in which to operate from as well. Absolutely fascinating. I was there nearly 60 years ago, and I may be able to share a slide. There we go. So this was, can you see that?
Yeah, we can see that.
So this was British Antarctic Survey expedition in 1965. And the Dexion you can see on top of the tractor there is ice depth radar. So we were traveling over a couple of kilometers of ice, and we were following, doing a survey of the rock bed underneath. And 10 of us were on that expedition. Just thought you might like to see that. It was very different.
It's absolutely fascinating to see. I think it brings it home, and I said that in our pre-chat a bit as well. It's like how privileged we are right now in terms of logistical support and what we can do now, right? We can actually even have a bit of comfort out there these days.
but the relief of getting, after a month of traveling several hundred miles of flatness and nothingness, which you described as particularly attractive, we finally got to the mountains, and it was just an enormous relief to actually see rock and stand on rock, as opposed to this eternal sea of ice.
Yes.
One question I wanted was what are you finding from this research? Is this the culmination of the slide you showed earlier, or are there new things that are appearing from the work you're doing?
So as you might know from your days as well, the actual scientific outcomes from expeditions like that always lag a little bit behind, right? So
Absolutely.
Getting there and doing the logistics and collecting the mud is the first big step. So we brought it back home now, and we just basically in last November started distributing all the individual samples from the first year to all our scientists. So we just start getting the first results on that. And I saw that there was a question in the chat as well in terms of what microbiology did we find. We can't fully answer these questions yet, but I can, for example, say that we we did some oxygen profiling of the sediments, and it's oxygenated down there below all that ice and kind of ocean. And the microbial community in the top part of the sediment column is definitely a community which derives kind of energy out of organic carbon, just like we know it in the open ocean environments. And if you then go further down into the sediment cores, you get to communities which live off sulfur and iron and more reducing environments. So that's really fascinating. We have a colleague from Australia who looks at ancient DNA, which is something I didn't know anything about before, but it's basically like our DNA, just, in the sediments. So you can look at what life lived there way back in the past, which again can tell us something about open ocean conditions or not. She has made the first analysis now and can say there is traceable ancient DNA in all our sediments. So again, now this has to be sent off for sequencing, and it will take a while till we get a scientific paper out of it. But yeah, all this science work is kicking off. So I can't really give you a new science story on this particular expedition yet. That will take a few years to come.
We will watch with great interest. And when you're drilling, you're going into the sediment, presumably as far as you can get before you hit rock.
So in this particular case, for the first site we went to, from the kind of geophysical observations, so from the seismic data we have, the layered sediment go well further than we could ever dream of drilling. So the time window, how far back in time we can drill or how deep we can drill, actually is determined by, we have this hole of 35 centimeter diameter. And even though we're circulating hot water within it, it slowly will refreeze as we go. So the amount of depths we can drill is basically determined by the time we can keep the hole open and operational. And that's where the 200-meter comes from. So that's a calculation that we can probably, if everything goes well, we can get up to 200 meters of sediment. So we wouldn't hit rock by that point. There's still sediment.
Right. Thank you. We've got a few questions here. Alan Grant, people would like to ask questions, he says. Oh, well, thank you. Or is that the one below? What microbiology did you find in the water or ice samples? Well, you partly answered that.
Yeah,
so we say anything else about that?
Yeah, so we tried to get water samples because Alan particularly asked about the water and the ice. So the water sampling, we couldn't quite get to work, so we didn't collect new water samples. We installed a mooring and do oceanographic observations, but no microbiology samples. The ice, we didn't sample at all. We just blasted through. So we were just interested in the sediment.
From DR Hurley, any comments on the fact that some chatter lately suggests temperature rise is actually higher than projected? Or is that built into your cat warming projections?
Yeah, it's a very good question. So I think so the projections I showed are not coming directly from our group. They just kind of done by climate modelers and publicly available to everybody. So we are definitely still within the window of projections of what we're seeing right now, but we're kind of on the upper end. And we've been on the upper end for a while. So that means when we look at these possible scenarios of warming by the end of the century, I think we shouldn't fool ourselves and think we're on the path of the best possible or lowest possible temperatures. The fact that we are seeing every year after year warmer temperatures is in fact a little bit alarming. And I always want to try to move that discussion into a positive space, because in the end, it's in our hands. We can make sure we don't let it get there, right? So it's not that we have to passively watch that. So that's the good part of the news.
Yeah, thank you. And from Alan Gilbertson, how do you know where you are? Satellites, question mark. Well, I can say how we used to know how we were. We plotted the theodolite in the sun. Yeah.
Amazing, yeah. No,
and of course, the sun went round and round above the horizon, so you could make it pretty accurate. But you were presumably working on satellites.
We're just working on satellites, yeah. So we did some geophysical installations where one part of the process is that you detect all the satellites you can get a signal from where you are. And that spot, that beautiful middle of nowhere spot where we were, we could get signals from 20 different satellites. So
Wow.
that's the way our world works today.
Did you communicate with the nearest living being above you?
Absolutely, because
Oh, did you?
the instrument you install then sends basically housekeeping data up to the satellite. The satellite sends stuff back, and then you press the button and say, "Okay, go." It's amazing.
No, I was talking about communicating with the space
Oh
station.
no, like actually talking. No, no, no,
That
no.
would be a step too far.
That's a step too far. We had a daily call in with Scott Base. That's what we did.
Yeah. And Mount Erebus didn't look too forbidding in your pictures. Did you try to go up in your spare time? Hmm.
I actually didn't, and they also don't let people go up Mount Erebus that easily. But around Scott Base, there's a whole area with a lot of really nice hiking trails between the New Zealand and American station, and you always have to grab a local guide to get like shown the tours first. You have to take a radio and all these kind of health and safety measures. But I was very fortunate to do quite a bit of hiking around the base station while you wait for your flights to either go north or south or wherever you're trying to go. But didn't go up Mount Erebus.
No, it's impressive. You could still see the plume on top of it, can't you? Almost every time there's a photograph, it's a small plume.
There's always a bit of smoke coming out of it. And it's interesting when you go to Scott Base. I'm sure it's like that at other base stations, but the New Zealand program operates a really nice program that everybody, all the scientists who stay, have to give like a science talk while they're there. So you learn about all the other projects going on. And there's always some microbiologist who, particularly microbiologists, who do work up on Mount Erebus because it's one of those great analogs for kind of microbes in extreme environments. And there's a lot of really cool work happening there.
Yeah, interesting. And did you see the historic bases there, Scott, Shackleton?
Yes, yes. I did that in my first year there. So we were lucky enough that this year actually, we were together with people from the Antarctic Heritage Trust, who, like, the whole team was just down there to basically do a tour of all the historical huts and do maintenance work.
Yeah,
And they gave a talk as well while we were there, and it, absolutely fascinating. One of the observations they shared I found quite interesting is as well, they do this every year, right? To just, preserve the history. And they said they have a lot more work because of the warming temperatures now, because some of the frozen stuff in the historical huts kind of starts sowing now. So it's a lot harder to maintain some of the things, but definitely got the privilege to see some of that, yes.
well, I believe that a few years back they found a crate of whiskey that Shackleton had taken out, and they replicated the taste of it. They got and when I took a party out of about 85 people in 2015, and one of the women brought a bottle. It was retailing at that time at 120 pounds a bottle, and I was asked if I would auction it, and I succeeded in selling it to an Imperial College alumni who was with us. He bought I think for £750, and the underbidder said, "Well, you didn't buy the contents; you bought the bottle. I'll pay another £75 and £750." So we raised several £1,000s on one bottle of Shackleton's whiskey. I'm sure he would have been proud of us.
Well done.
Now, keeping in mind, do we always drill in the same hole?
Um, so the target for this particular project was just to drill one deep hole. But in the first year, well, we very quickly realized that we couldn't drill a deep hole, and we had just an open hole through the ice. We got like 10 short cores, and we asked ourselves that question as well. What is the likelihood lowering a tube with a weight on top through 600 meters of ice and water, and hit exactly the same spot on the seafloor so that you drill
Yeah.
into your own old hole. I can tell you from doing 10 short punch cores that year, we didn't. Because you would see it, right? You would see that it's disturbed or like a different stratigraphy or so. And we actually got 10 very similar looking cores, which means the 50 meters of ocean are enough that kind of on your cable, you go a bit like right, left, like you
Yeah.
don't quite hit exactly the same spot. But in
Be-
theory, we just want to have one hole.
yes, in theory, yes. But the ice is moving as well.
It's moving as well, but very slow. So it's a part
Ah,
of the Cycle Coast, which is where the ice streams are stagnant right now. So the Camp ice stream stopped flowing 150 or 180 years ago. So there's a whole different interesting story behind that. But that's why we picked that particular drill site. So it's stagnant.
yeah. And can you use solar power, says Alan Gilbertson.
We totally can. So we had solar power for a bunch of our equipments, and a lot of people used kind of chargers with solar panels for their phones or stuff like that. So absolutely, the because it doesn't get dark, that's a good resource. It does
Yeah,
get
yeah.
cloudy though, but when the sun is out, it's very powerful. So you totally can.
Are you using this for equipment or for your privately for your phones?
Mainly for our personal gear. So we had really good discussions, and there's a lot of effort happening on the logistics side from Antarctica, New Zealand. So of course in the base station they use solar power to operate things as well. There's a wind farm as well. So there's a very strong move to renewable energies in the base stations. And for some of the operations. But like for example, our whole drill system is that wasn't there yet, so we used kind of fuel for that one.
Yeah. Is the goal of the project to collect samples and then see what you've got, or is there a predetermined goal? How far back in time have all the drillings taken us?
That's a wonderful question. I think it's a little bit of both of that. When you write your initial proposals to get money to do some of this science, you of course say, we will go and bring back sediment, which is 100,000 years old or 3 million years old to hit all these particular time periods, which were a bit warmer in the past and you want to get. And you back that up in some of the observational data from the geophysics you collected before. But I always say that's a little bit geofantasy. What you actually get is you only know once you drill, right? So there is a
Yeah,
little
yeah.
bit of actually having to drill the hole to see what you get and what age sediment it is. In terms of how far back in time the drilling has taken us, it's very different. So around that part of Antarctica where we are, underneath the ice, the drilling hasn't taken us further back than the last glacial maximum, so 20,000 years ago. And that's exactly why we want that deep drill core, because if you go to the last time when it was really cold in Antarctica and the ice was extended, what the big ice sheet does, it bulldozes basically over a lot of the sediment and really compacts it. So the sediment from that time is very stiff. So when
Yeah.
you just put like a little weight down there, it will always bounce off that layer. And that's why we needed to bring a big drill rig down there to actually get through it. And we hope then to get into the older sediments.
Thank you. I think we're going to be wrapping this up shortly, so let's see if we can get through the last of these questions here. Keeping in mind the natural cycle of global temperature change, has anyone done any research into how much of the present climate change is due to human activity?
Yeah, that's a great question as well. So the climate, of course, has always changed naturally as well. And then there's on top of that what we as humans do now. And I can just refer to all the reports from the Intergovernmental Panel on Climate Change, which puts together all the facts from all the science community every few years. And there is what we call attribution studies, which really show that over the last 150 years, most of the warming we observe is human induced. So for that time where we're pumping a lot of CO2 into the atmosphere, there's a clear correlation with the temperature rise. So we can very clearly say that.
We can separate it. Yeah.
Yeah.
I see somebody has flagged up Martin Siegert, who I'm sure you know.
Absolutely.
Gave us a fireside chat three years ago, something like that, 4 years ago, during COVID, I seem to remember.
Oh,
But I met Martin on a number of occasions through Antarctic clubs and things.
yeah. No, we co-supervise students and do projects together. I
All
do
right,
know him well.
excellent. And Robert Williams here, how do you prevent drilling water contaminating sediment?
Oh, excellent question.
Ooh.
This is for the
Well,
microbiologists to
well, you
worry
are at a
about.
firside chat with Imperial College. You expect
Absolutely. Yeah, yeah, no,
hard
that's
questions.
true. Why am I surprised? You're absolutely right. So the idea there is that for the microbiology samples or anything which is contamination prone, once the sediment comes up, you carefully sample just the interior of the drill core, not anything around the outside. So you can't totally prevent it from getting in touch with the drill mat, but you sample the drilling fluid, analyze that, and then sample the interior of the core and compare, and hopefully can separate the two signals.
Thank you. And how long has this project been going on? What
So
have
in
you
terms,
been? Well, it's a couple of years, isn't it? Or is it even longer?
So it's a couple of years that we've been going to Antarctica now, but actually the preparation for this project started 10 years ago, was doing geophysical surveys and establishing the route to get out to our site, looking for crevasses and all of that.
All
So
right.
it's been in the making for 10 years.
And Keith says, I did a geophysical MSc in 1975. You inspired me to keep up. What a wonderful experience you must have had. Hope the temperature stays low. Keith, you should go out there for yourself. That's the answer to that.
Absolutely.
And do you have any Russians in your team?
No, I think we don't have any Russians in our team right now, but that is not by design. In principle, science is open to anybody, but Russia is not one of the financially contributing countries to this project.
And whether there is anybody from Ukraine. Ukraine certainly have a base in the Antarctic,
Yeah,
and so do Russians. My experience when I was down there was that all nations collaborate 100%,
absolutely.
particularly in terms of when there's illness or danger or an accident. Uh, Everybody helps, including at times when we're at war with Argentina.
Absolutely, Rod. I can only second that. It's very collaborative, and people are just people down there and doing science, and that unites us all.
Well, and the Antarctic Treaty spells it out that it's only to be used for scientific endeavor, and so far it's been working. Well, Tina, thank you so much for an absolutely stunning talk. I should have worn a sweater, I guess, at the very thought of it. But thank you very much. Everybody's been cheers and somebody's clapping. Before we go, just like to thank all of you who have come along, particularly supported us in your various ways. Azad and Regina Ayub for their particular contributions to our activities. I'd also like, before I wind up, to say that the next event is on Friday, the 20th of June, when Stuart Martin is going to be talking about developing space-based solar power. So we hope to see you then. But thank you, Tina. If everybody would like to undo their buttons and show themselves, we can thank you very much in the usual way.
Okay. Bravo. Great talk.
Thank you so much, everybody, for coming and attending and asking absolutely excellent questions. What a privilege.
Thank you. Bill, do you want to add
you.
anything to that?
No, all good, thank you, and very much appreciate, or firstly, Rod, for your chairing of our fireside chat, and obviously Tina for your contribution. And maybe we can invite you back in a couple of years to pick up on the science that's kind of resulting from your work.
Very
And,
happy to come back.
I liked the comment in the chat saying we hope the temperature keeps low. So
Yeah.
and good luck in your next endeavours.
Yes, absolutely. Thank you so much.
Thank you,
Thank you, everybody.
Thanks very much.